Welcome to the office. We want to take a look at factor groups here. And in this example, we are going to take a look at something that is pretty similar to our previous example. Similar, but not the same. In our last example, we considered, let's scroll back a little ways here, we considered the factor group Z mod 12Z. And we said, all right, through this isomorphism, we can say that this is isomorphic to Z12, and that told us about the size of the group, so we didn't have to do too much work there. And that was pretty nice, pretty fun. But in this next example that we want to consider, we're not considering a homomorphism, and that's not, so we're not going to get this nice isomorphism to tell us about the structure of the group. So we're going to have to kind of dive into this a little bit to see if we can figure out what's going on, just to help us get a good image. All right, so for the factor group Z24 mod, what's generated by 6. Okay, that's a little bit interesting. It's maybe worth noting that what's generated by 6 is going to be exactly 0, 6, 12, 18. So we know that we already know that that element has an order of 4. We should be familiar with that. 6 times 4 gives us 24, which would be 0 in Z24. So that should make sense to us. We don't have to write it down to be able to observe that. This is just a nice reminder for us. What we want to do is we want to find the order of this group. So Z24 is finite, which is wonderful. This allows us to use the content developed for proving Lagrange's theorem. All right, so we need to recognize a couple of things here. We need to recognize that Z24 mod, what's generated by 6, is the cosets of 6. And what we developed in order to prove Lagrange's theorem was that the order of the group G is equal to the number of cosets times the order of the subgroup. And because we have that it's finite, then we can actually, right, this is a perfectly well-defined equality. Finite number equal to number times number. There's no issues there. So the order of the group that we're interested in this case is the order of Z24 mod, what's generated by 6. Now the number of cosets of this is, right, so it's, I'm sorry, that's not what I wanted here. This is what I want to find. This is the number of cosets. There we go. Sorry about that. This is the number of cosets of what's generated by 6. And what's generated by 6 has 4 elements, of course. We looked at that. And Z24. There we go. So we know that these that this equality holds. Multiplication here, if you choose to write that symbol there. The Z24, of course, has 24 elements in it. This is the thing that we are interested in finding. And we already said that this has 4 elements in it. Divide both sides by 4 to get the size or the order of the factor group. Oops, I missed my 24 here. Z24. The order of this group is exactly 6. Okay, the number of cosets is exactly 6. That's what we were looking for, and we can perform that computation because Z24 is finite. And again, that's content that we developed in our discussion leading up to Lagrange's theorem. All right, now the question is, we want to find the order of this particular element. And that's maybe a little bit annoying for us to try and really understand easily. So maybe what's helpful is for us to take a brief look at what are the elements of the what are the congruence classes. So I'm going to grab onto just a list of the elements in the original group Z24. So we have 0, 1, 2, 3, 4, 5, 6, 7. Let's see here, 8, 9, 10. Let's see here, use commas still. 8, 9, 10, 11, 12, 13, 14, 15. And this is going to end up taking too much space. So let me change our size here. Let's try for 12-point font and move this over. Here we go. 16, 17, 18, 19, 20, 21, 22, 23. Boom. Yes, there we go. That gets us what we're looking for there for space. So I might notice first that 6, what's generated by 6 is one of the cosets. So 0, 6, 12, 18, that creates one of the cosets. Another coset is going to be what happens when I add 1. So I get 1, 7, 13, and 19. That's another one of the cosets. Then I could add 2, and that's going to get me another coset. So what I'm pointing to here gives us exactly the coset. So 2, 8, 14, and 20 all give us one coset. So if I want to talk about 2 plus what's generated by 6, that's the same as talking about 8 plus what's generated by 6, which is the same as 14 plus what's generated by 6. And that's exactly what we have here. To finish it up, we could continue on and add 3. So 3 gets us 3, 9, 15, 21. So those 4 elements create another coset. And let's go with orange. Oh, this is kind of a interesting orange. Yeah, I'll go with that one. Add 4 here. So 4, 10, 16, 22. That gets us something different again. And then finally, I can add 5 to identify our final coset here. So those are our cosets. Those are the 6 elements that we're working with in this group Z24 mod, what's generated by 6. So if I want to find the order of this element, what I'm looking for is I'm looking to add it to itself sufficiently many times that I'm going to get either 0, 6, 12, or 18, right? Multiples of 6. So what I want to do is I want to recognize that, let's see here, the identity element is what's generated by 6, or 0 plus what's generated by 6, or k times 6. I'm sorry, that's supposed to be an equals. There we are. K times 6 plus what's generated by 6. Any multiple where k is an integer. Could be positive or negative. And right, technically we can start to go outside of that, because I can then talk about 24, but 24 in Z24 is 0, and that lands me back in here, right? So I have the ability to extend beyond that. And what I want to do is I want to notice that So notice that n times 14 plus what's generated by 6 is going to give me exactly n times 14, n times 14 plus what's generated by 6. And what I want to find is find the least n in here such that n times 14 plus what's generated by 6 is equal to what's generated by 6. Now, in order for us to do that, right, I'm really looking for this to be k times 6 plus what's generated by 6. To find the least, I just need to find the least common multiple of exactly my two numbers, right? N times 14 and k times 6. I'm looking for the least common multiple of 14 and 6. They both have a factor of 2. This has a factor of 7. This has a factor of 3. So 2 times 3 times 7 is going to give us 42. So the least common multiple is 42, so I can choose k equal to 7. So this is going to give us n times 14 is equal to 42. 6 times 7 gives us 42. And then n must be equal to 42 divided by 14, and that would be 3. So the order of the element 14 plus what's generated by 6 is 3. And there's essentially, right, to confirm this, we could do two different things. So just a little bit of side work here for some confirmation. I can take n times 4, sorry, I'm saying the order is 3. So I can take 3 times 14 plus 6, what's generated by 6. Again, that's this thing added to itself 3 times, or 3 times 14 plus what's generated by 6. 3 times 14 is 42 plus what's generated by 6. But this is 0 mod 24, not mod 24, mod 6, right? That's where I'm working at here. So this is 0 plus 6, or just 6. If I wanted to observe this as just trying to work up to it to observe that it is, in fact, the least. So it itself is not the identity. 2 times it is equal to, right, 14 plus 6 plus 14 plus 6. That's 28. 14 plus 14 is 28, plus what's generated by 6. And then if I wanted 3 times that, I'm going to take that 28 plus what's generated by 6 and add another 6 plus what's generated by, 14, what's generated 14 plus what's generated by 6. And that again is 42 plus what's generated by 6. But this is 0 plus what's generated by 6. And again, that's me recognizing that what gives me that 42 is equal to 0? Well, my identity element is all of the things that are multiples of 6. And that is indeed a multiple of 6. So that's just us trying to observe or verify that our computations here did in fact give us what we were looking for. Now, you might feel that this is a little bit weird, and you're like, well, Dr. Ryan, how is it always this way? Is it really always that simple? Is it always just the least common multiple? Well, mostly, yeah, right. That's kind of what we were developing earlier, even when we talked about taking the direct products of groups, right? We're seeing that same sort of relationship occurring here, same sort of relationship. But in our next example, we're going to take a look at something that is not just right, nice integers mod something nice integers. What we're going to do is we're going to take a cross product and mod it by some subset, and that cross product is not right. It's not those nice integer or modulo groups. So join back in the office here for another excellent example.